So far, in our discussions of graphing, we've considered data obtained from one variable, either categorical or quantitative, and we've learned how to describe the distribution of that single variable using the appropriate visual displays, as well as numerical measures of center and spread. Next, we're going to be visualizing our association of interest by exploring the relationship between two variables.
Recall that our basic research question is simply whether or not two variables are associated with one another. So is there a relationship between gender and test scores?
Is there a relationship between the type of light a baby sleeps with and whether or not the child develops nearsightedness? Are the smoking habits of a person related to that person's gender? Or how well can we predict a student's freshman year GPA from his or her SAT score? Before we test our own association of interest with inferential statistics, we're going to work on visually describing that relationship. It's important to understand that when studying two variables, each variable has a role to play. That is, a variable may either be a response variable, also known as the dependent variable or outcome variable, or it could be the explanatory variable, also known as the independent variable or predictor variable.
At this point, I'm going to be asking you to impose a causal model on your research question. To do this, you'll need to designate which of your variables is the explanatory variable and which is the response variable. Note that we can only impose a causal model rather than actually test for causation because we're working with what's known as observational data. In other words, the data sets that we're using are based off studies where the sample is simply observed rather than being manipulated or influenced in any way, as it would be in an experiment. Even though we won't be able to be certain that the association we're testing is causal, for the purposes of exploring our question, it remains important to determine the role that each variable will play in our model.
This role type classification can be summarized and easily visualized in this table. This classification system serves as the structure for the rest of this course. You'll find that not only does it help you to construct graphs, but it's also the basis for selecting statistical tools that can be used to explore the relationship of variables that you're interested in. The tools for statistical analysis and for visually representing the relationship between variables is based on the role and type of each variable, whether response or explanatory, and whether categorical or quantitative. To get the hang of this, let's go back to some examples and determine which of the role types represents each research question. If we want to explore whether the outcome of the study, the test score, is affected by the test taker's gender, we would designate gender as the explanatory variable and test score as the response variable. If we want to explore whether the nearsightedness of a person can be explained by the type of light that person slept with as a baby, light type would be the explanatory variable and nearsightedness would be the response variable. If we're examining whether a student's SAT score is a good predictor of their GPA freshman year, the SAT score would be the explanatory variable and the freshman year GPA would be the response variable. If we want to see whether a person's pass-fail outcome on a driving test can be explained by the length of time that they practiced driving prior to the test, time would be the explanatory variable and driving test the response variable. For our sample research question, we've decided that smoking will be the explanatory or independent variable and nicotine dependence the response or dependent variable. More specifically, we're interested in the level of smoking at which nicotine dependence is experienced. How do we examine the association between two variables graphically? When we graph the association between two variables, the independent or explanatory variable is plotted on the x-axis. The dependent or response variable is plotted on the y-axis. This is a most important convention to use when graphing relationships. However, before we actually construct our graph, there are a few questions we need to ask about the types of explanatory and response variables that we'll be working with. The first question is, what type is the response variable? Is it categorical or quantitative? For our sample research question, the response or dependent variable is nicotine dependence, which is categorical. Next, we need to determine how many categories are in this response variable. Since nicotine dependence is coded 1 for yes or present and 0 for no or absent, we have 2 categories in the response variable. The next question to ask is, what type is the explanatory variable? The explanatory or independent variable is number of cigarettes smoked per month. As we saw in the demonstration of histograms, this is a quantitative variable. Since it won't be visually meaningful to examine a bar chart with a quantitative explanatory variable on the x-axis, when our response variable is actually categorical, before we start to graph, it's important to bin our explanatory variable into categories. That is, in order to visualize the relationship that we're interested in, we need to add some data management that will allow us to construct a C2C or categorical to categorical bar chart. To convert a quantitative variable into a categorical variable, we begin by looking at the frequency table for the explanatory variable, number of cigarettes smoked per month. We could use the cumulative percent column to make decisions about grouping individuals into quartiles, roughly 4 equal groups in size, or even quintiles, 5 equal groups in size. However, in this case, it seems a better decision might be to create more meaningful smoking groups based on specific quantities. Cigarette packs contain 20 cigarettes each. We're going to create a new variable that estimates the number of packs that each individual smokes per month rather than the number of cigarettes. This could be a step closer to a categorical variable that's meaningful. Returning to the program, we add the following syntax. $1 $packs per month, assignment arrow, $1 numsigmo_est/20. The new variable is called packs per month, and it is set equal to the number of cigarettes smoked per month divided by 20. We're going to add a second command so we can view the new frequency distribution using freq function. You'll see that we're using the freq function and the as.ordered function also. Parent data.plot.bivariate2 $daily close parent. Now we're ready to plot. Again, we use the ggplot and stat_summary commands with the variables identified for the appropriate axes and complete with labels. Remember our categorical response variable. To create this new secondary variable, we tell R, for those observations where packs per month is less than or equal to 5, then pack category, our new variable, is coded as a 3. We chose 3 because it's roughly the quantitative midpoint for this category. We use similar statements for the remaining categories. So observations corresponding to packs per month greater than 5 and less than or equal to 10 get a value of 7 in the variable pack category, again, roughly the midpoint. Then, when packs per month is greater than 10 and less than 20, pack category is coded as 15. Next, for observations where packs per month is greater than 20 and less than 30, then pack category is 25. And finally, for observations where packs per month is greater than 30, then we assign a 58 to the corresponding observations in pack category. Again, if we examine the frequency distribution, 58 is roughly the quantitative midpoint. And as always, we use the freq function to examine the distribution of our new pack category variable. The last thing we need to do is categorize the new pack category variable using as.factor function, since our new variable is categorical. We saved it. Now I'll highlight these lines and click Run. First, we need to load the library which contains the ggplot and geom_point functions, which is ggplot2. Next, we want to create a small data set for plotting our variables, just as we did for our bar graphs. Our point function takes the usual aesthetics inputs, which tells R first the variable you want to appear on the x-axis, which is the explanatory variable, followed by the variable that you want to put. When graphing the relationship between a categorical explanatory variable and a categorical response variable, we will first create a small subset of our data that we'll use only for plotting these two variables. We create a small subset containing only the unique identifier and the two variables we'll plot, and then use the function na.omit to remove all rows with missing data so that they will not be plotted. The following code creates this dataset and calls it data.plot.bivariate1 to indicate that this is the dataset for our first bivariate plot. One last data management step we need is to change the storage type of the response variable. Right now, it's correctly coded as categorical. However, we need to change the storage type to numeric. R requires the response variable to be numeric in order to calculate the proportion of the sample diagnosed with nicotine dependence. It's very important to note that this is only for the purpose of plotting and should only be done on the plotting dataset data.plot.bivariate1. It should never be done on the original dataset, data or sub1. We can do this with the following code. Data.plot.bivariate1 $tab12mdx assignment arrow as.numeric parens as.character parens data.plot.bivariate1 $tab12mdx close parens. Note that we don't directly change from factor to numeric. We have to use as.character as an intermediate to preserve the correct values in the variable. Now we're ready to plot. As always, we start with the ggplot function and supply the dataset that we wish to plot, in this case data.plot.bivariate1. Then we add the function stat_summary and identify the variables that go on the x and y axes in the aesthetics command. Then we specify that we're calculating the mean value of the response variable by each level of the explanatory variable, and we specify a bar plot. This produces the plot, but to make this plot more interpretable and appropriate for presenting our results, we should add labels. The axis and main title labels can come in any order after you specify what it is that you're graphing. Here's our categorical by categorical bar chart. Pack category, our explanatory variable, is on the x-axis, and this is by the rate or proportion of nicotine dependence along the y-axis. So you can see from this graph, among those smoking 1 to 5 packs a month, about 25% of those individuals are nicotine dependent. Among those smoking 6 to 10 packs a month, 50% are nicotine dependent. Among those smoking 11 to 20 packs a month, 58% are nicotine dependent. Among those smoking 21 to 30 packs per month, almost 70% are nicotine dependent. And among those smoking more than 30 packs a month, more than 70% are nicotine dependent, around 77% here. We can also see that these rates form a pattern. That is, the more packs smoked per month, the higher the rate of nicotine dependence. So in a graphical way, we're already seeing that there seems to be a relationship between smoking and nicotine dependence, just as we hypothesized. Looking at our graphing decisions chart, we can see the steps we've taken to generate a bivariate graph with a categorical response variable that has 2 categories and a quantitative explanatory variable. We also discussed how to convert the quantitative explanatory variable to a categorical variable, a step which must be taken for the purposes of visualizing the relationship. If our explanatory variable was originally categorical rather than quantitative, we could have skipped this step and just moved on to a categorical by categorical bar chart. What decisions need to be made if the response variable has more than 2 categories? In this case, we would need to collapse a response variable categories into two categories. To demonstrate this, we'll have to modify the research question. So let's modify the research question to look at the association between ethnicity and smoking stage. And we'll create a response variable that categorizes young adult smokers into three groups: non-daily smokers, daily smokers, and those with nicotine dependence. These are the ethnic groups recorded in the NESARC codebook, as well as the syntax that we can use to create a three-category smoking stage variable. We create the new secondary variable, smoke group, inside our dataset and assign it the appropriate value based on an individual's values on another variable. We make it into a factor because the values 1, 2, and 3 are dummy codes for this categorical variable. This sample can be described with these three smoking categories. This univariate bar chart shows that about 50% of the young adults sampled are nicotine dependent, about 30% are daily smokers without nicotine dependence, and almost 17% are non-daily smokers. However, to examine a relationship between this variable as the response variable and another, we need to collapse this to only two categories. To do this, we need to make some decisions. Here are two perfectly reasonable decisions that we could make. We could examine the association between ethnicity and daily versus non-daily smokers, or we could examine the association between ethnicity and nicotine-dependent versus non-nicotine-dependent individuals, thereby collapsing across these categories in some way. In either case, some data management needs to be added to the program. To collapse the response variable into daily versus non-daily smokers, we use this syntax. We recode each level of this new variable one at a time. For observations corresponding to S3A Q3B1 not in A and S3A Q3B1 equals 1, that is, if the individual smokes 30 days a month, then daily gets set to a value of 1. For observations corresponding to S3A Q3B1 not in A and not equal to 1, then daily gets set to a value of 0. Finally, the last step first categorizes the new daily variable and then attaches this categorized variable to our new dataset. To graph the relationship between a categorical explanatory variable, ethnicity, and a two-level categorical response variable, daily smoking, we will first assign meaningful labels to our ethnic group categories. In order to more easily create a descriptive, fully labeled graph, a first step before graphing is to create a variable for eth_2a that contains descriptive labels instead of dummy codes. When working with the ggplot2 library in R, ggplot2 uses labels from the actual variable. So the only way to label the graph is to have a variable actually coded with the labels we want. We need to consult the codebook to translate the dummy codes and then perform data management that reassigns the dummy codes as descriptive labels. Going back up to the data management part of our code, we create a new section that's for relabeling the values in factor variables. First, we find out what the levels are and what order they're in. To do this, we use the code levels parens sub1 $eth_2a in parens. This is important because when we rename the different levels, they have to be in exactly this order, and there has to be a new string given for each existing level. Looking back at the codebook tells us which strings to use. Here, we append .c onto the end of the variable name to indicate it's coded, but you can use whatever convention works for you. So our new variable, ethrace2a.c, is assigned to be a categorical version of the original ethrace2a, but with new labels for the levels. Again, this is where the ordering of the levels is important because R matches up this set of strings to the existing levels. Keep the new labels in the same order as the original ones. Now that our ethnicity variable is coded as meaningful labels, we're ready to create our data subset that we'll use for plotting. Again, this contains the unique identifier and both variables will plot and removes all the rows with any NAs. We're going to call it data.plot.bivariate2. The last step is to convert the response variable into type numeric so that the proportion can be calculated. As explained earlier, it's important that this step is done only on the small plotting data set. Data.plot.bivariate2 $daily assignment arrow as.numeric parens as.character parens data.plot.bivariate2 $daily close parens, close parens. Now we're ready to plot. Again, we use the ggplot and stat_summary commands with the variables identified for the appropriate axes and complete with labels. Remember, our categorical response variable should not have more than 2 categories or levels, and those 2 categories should be coded as 0 and 1. 0 represents no or negative observations, and 1 represents yes or positive observations.
Because our response variable was categorical with more than 2 categories, we needed to collapse it into only 2 categories. And because our explanatory variable, ethnicity, was categorical, we created a categorical by categorical bar chart. Had our explanatory variable been quantitative, we would have needed to bin or collapse that variable into categories before creating the categorical by categorical bar chart.
From the 2 bivariate graphing examples that we've covered, we filled in the left side of our graphing decisions flowchart. Each example showed situations when our response variable was categorical. Let's talk now about the right side of our flowchart when the response variable is quantitative. We'll now change our research question using an example from the Gapminder dataset. Here, we're interested in the association between the percent of the population living in urban settings within each country and the country's rates of internet use. That is, the percent of people with access to the World Wide Web. Below, you can see a full description of these variables from the Gapminder codebook. For this research question, both the response and explanatory variables are quantitative. A bar chart would not work here. The graph of choice would be a scatterplot. A scatterplot, by definition, is a graph of plotted points that show the relationship between 2 quantitative variables. In a scatterplot, data for each observation's explanatory and response variable are plotted. This scatterplot shows a sample of 11 observations according to the relationship between height and weight. In the lower left-hand side of the graph, we see plotted individuals with relatively low height and weight. In the upper right-hand portion, we see individuals with relatively high height and weight. Returning to the Gapminder dataset, let's see how we can use R to examine the relationship between percent of the population living in urban settings and the rate of internet use. Since we're using a different dataset, we'll begin with a new program. We'll save our work on the script and then clear the console by clicking on Edit, then Clear Console, or you can click Ctrl-L. We'll clear the plots by clicking on the broom icon in the Plots window, and then clear the Global Environment workspace by clicking on the broom icon in the Global Environment window. You can also clear this workspace by typing this code in your script or editor window: rm parens list equals ls parens in parens. First, we set the working directory. We include the library statement for the package DESCR. We include a new line of syntax, options, parens, digits equal 3 in parens, which will limit the number of decimal places shown. Now we load the Gapminder dataset. To give us a familiar dataset name to work with, we assign the loaded dataset to data. Then, we add syntax that will let us look at the central tendency and spread or variability of both urban rate and internet use rate. The summary function tells us about the range of these variables, as well as their median and mean, while we have to separately request the standard deviation and tell R to ignore NAs when doing the calculations. We can see that for urban rate, the mean percent of the population living in urban settings is about 57%. The standard deviation is about 24%, suggesting that there's quite a bit of variability from country to country in terms of the proportion of the population living in urban settings. For internet use rate, on average, about 35.6% of the population across these individual countries has access to the World Wide Web. Again, with a standard deviation of 27.8, there seems to be quite a bit of variability from country to country. But is there a relationship between these two variables? We can explore this question visually with a scatterplot. R provides scatterplots in response to the ggplot and geom_point functions. First, we need to load the library which contains the ggplot and geom_point functions, which is ggplot2. Next, we want to create a small data set for plotting our variables, just as we did for our bar graphs. Then we use the function na.omit to remove all rows with missing data so that they won't be plotted. The geom_point function takes the usual aesthetics inputs, which tells R first the variable you want to appear on the x-axis, which is the explanatory variable, followed by the variable that you want to put on the y-axis, which is your response variable. Before we run this graph, we need to add descriptive titles. R will create default axis titles based on the names of the variables you provide, but these can be cumbersome, and it's not always clear what these variable names represent, so we need to provide axis labels that are descriptive as well as a main title. To characterize the relationship that we see in a scatterplot, it can be helpful to draw a line of best fit through the observations as a way of trying to determine how the dots line up. That is, do they seem to line up in a positive or negative direction, or with a positive or negative slope? An increasing slope, as we have here, between urban rate and internet use rate, indicates the relationship is positive, That is, an increase in one of the variables seems to be associated with an increase in the other. Here's another example from Gapminder exploring the relationship between income per person in each country and internet use rate. Again, if considering a linear pattern, the relationship seems to be positive. That is, higher income is associated with higher internet use rate. The strength of the relationship in a scatterplot is determined by how closely the data points follow the form. In this scatterplot, the data points follow the linear pattern quite closely. This is an example of a very strong relationship. In this other scatterplot, the points also follow the linear pattern, but much less closely. Therefore, we can say that this is a weaker relationship. The form of the relationship is its general shape. When identifying the form, we try to find the simplest way to describe the shape of the scatterplot. There are many possible forms. As we saw, a positive or increasing relationship means that an increase in one of the variables is associated with an increase in the other. And negative or decreasing relationship means that an increase in one of the variables is associated with a decrease in the other, as shown in this central scatterplot. Not all relationships can be classified as either positive or negative. Further, if you can't plausibly put a line through the dots, if the dots are just an amorphous cloud of specks on the graph, then there may be no relationship.
For various reasons, a scatterplot is sometimes limited in its ability to allow us to evaluate a relationship visually.
Here's a scatterplot for income per person by rate of HIV among 15 to 49-year-olds. Since most countries have a low HIV rate per 100 people, the dots on this scatterplot seem to clump in the lower left-hand corner of the graph. So to try to get a better sense of whether or not there's a relationship between these two variables, we would try to categorize or group the explanatory variable income. The summary function tells us the value of the variable at the 25th, 50th, and 75th percentile or quartiles. The 50th percentile is the median. If we wanted other percentiles, we could have used the freq function. This summary function output for the Gapminder variable income per person will allow us to divide the countries of this data set into 4 ordered groups according to income per person. We then can add this data management to our code to make the new variable income group. After saving the script and running these lines of code, along with running a frequency distribution on the new variable, we can see the distribution for income group. Our 4 ordered groups have 47 or 48 countries in each income group. Remember, the highest income group, 4, has the highest 25% of the countries in terms of income per person.
With this new categorical explanatory variable, we're now ready to create the last type of bivariate graph. That is, the categorical to quantitative bar chart.
Just as we've done with earlier bivariate graphs we've plotted, the first step in making the quantitative to categorical bar graph is to make the table of values we want to plot. For this bar graph, our data subset for graphing will be called data.plot.bivariate4. We'll first define it by omitting NAs from our variables. Then we use the function ggplot followed by the function stat_summary. As always, we follow these functions with the labeling functions. In this bar chart, while we can see clear differences in HIV rate based on income per person within countries, the relationship does not seem to be linear. Although we might have expected a negative linear relationship, that is, increases in HIV rate with decreases in income group, you can see in this graph that income group 2 falls outside of this pattern. We've worked through each type of bivariate or two-variable graph, highlighting when and how each should be used to visualize a relationship. Now, let's just very briefly summarize. When visualizing a categorical to categorical relationship, we use a bar chart with explanatory categories on the x-axis and the proportion of our response variable on the y-axis. When visualizing a categorical to quantitative relationship, we use a bar chart with explanatory categories on the x-axis and the mean of our response variable on the y-axis. When visualizing a quantitative to quantitative relationship, we use a scatterplot, in which each observation is displayed according to the values of the explanatory and response variables.
Use these basic guidelines, as well as the Graphing Decisions flowchart, to visualize the relationships between your own variables of interest.